hang on, yeah.
It's already up.
I don't think I can talk for 5 minutes. I don't have enough knowledge with me. But I think I'll just hand over to Prof. Weibel.
So let me start with a quiz. How many of you are interested in K-theory of rings? How many of you are interested in K-theory of varieties? How many of you are interested in K-theory of derived categories? So how many are interested in K-theory of rings? Varieties? Derived categories? Okay, thanks. A?
Is this your planning then?
Well, you know, one doesn't know the level to start at. So it's good to see you, Rob. So my understanding is that about this level I can't write because the people in the back can't see. So I'm going to put stuff here and then raise it up. So so the two things that I want to start off with are the K-theory of rings and the K-theory of varieties. In the K-theory of rings, mostly deals with K-theory of projective varieties, but we can also talk about the K-theory of the finitely generated R modules. And people always wonder left modules or right modules. I don't really care, but I'm going to think left modules in my head. So if I do something that looks weird, that's what's in my head. For varieties, we can do the same thing. We can talk about vector bundles, or we can talk about coherent modules. So the K-theory is based on this sort of a basic understanding, but then so if I write projective modules as a P with an under subscript R, then the bounded chain complexes of projective modules are a thing that one can look at, and one can similarly do this, and these are called perfect complexes. And strictly speaking, I should say strictly speaking complexes. And here we have bounded chain complexes of coherent modules over a nice scheme. So we can do the same thing here. And one should probably stick an FG to remember that these are finitely generated. So this is the basic fabric that we are thinking about when we talk about K-theory. Now I'm going to assume that everybody in here has seen this before, so I'm going to write it on the board that you can't see. So if you're given an abelian monoid, so for example, a class of projective modules up to isomorphism, you can form an abelian group. And if you do this to this one, you get K0 of the ring. So how does one form the abelian group? Well, I can write down a formula that you've all seen before, but the basic idea is that it's the universal abelian group that this monoid maps to. So it's so this is a construction, and this is works for any symmetric monoidal category. So in other words, you have the notion of of an operation, which in most applications for us is going to be direct sum. The direct sum is associative up to coherent isomorphism, and so on. One of the axioms is that there's a canonical isomorphism like this. So if you take any symmetric monoidal category, you take the isomorphism classes of objects like this, they form an abelian monoid, and you can take the group completion, and that would be K0. So that is the way that K-theory was thought of back in the 1960s. So now let's go over here. So the basic framework that we work with is that we work with something like an additive category. And so what is this? This is a category which is a subcategory of an abelian category. So this category lives inside of an abelian category, and it's closed under extensions. So what's an example of such a thing? Coherent modules is an abelian category, so it's a subcategory of an abelian category. Vector bundles is a subcategory of coherent modules, and it's closed under extensions. Projective modules is closed under extensions in the category of all finitely generated modules. Now there's a technical glitch that I'm sliding over, I'll just say it, and that is when you talk about finitely generated modules, you should always assume your ring is Noetherian. When you're talking about projective modules, one doesn't worry about that. When you have a non-Noetherian ring, there's a way to get around this, and you just replace the word finitely generated by the word coherent, and you hope that you know what you mean by the word coherent. I'm not going to explain that at this lecture because that's just a technical sidetrack. So if you have an abelian, an exact category, then there's something called a Quillen construction. That one uses to work with K-theory. If you think about more general situations, then we have something like the notion of a Waldhausen category. So over here, when we work with projective modules or coherent modules or whatever, that corresponds to the Quillen construction. And we go over here and we work with chain complexes, that usually corresponds to the Waldhausen construction. So what is a Waldhausen construction? So you have a notion of a weak equivalence, and because that's a really long expression, I will typically write an arrow with a little tilde over it to mean that this is a weak equivalence. And you have a category of cofibrations. So this is also a subcategory. And we have the assumption that the 0 into A is also a cofibration. And then we have gluing and push-out axioms. So they're rather long and complicated if you write them out in words, but basically what happens is if you have a cofibration and you have a map from here to C, then the push-out map is a cofibration. And if you try to draw a horrible diagram, I'll draw it here and then I'll erase it very quickly. So if I take this situation, and I take A prime to B prime, I take this to C, take this to C prime, and I have a commutative diagram like this. Is there colored chalk? Yes, there's colored chalk. So one can take the push out here, and one can take the push out here, and well, there's a natural map like this. Let's see, one can take this, and one can take this. Somehow or other okay, so now we have something that's supposed to look like a square. Somehow or other, this is like an Escher drawing. I think I can't see the bottom from the top. But the point is that if you assume that this is a weak equivalence, then the assumption is that that's a weak equivalence as well. So the push-outs. Okay, so this is where you're supposed to not be colorblind. So the white tilde goes with the white arrow, and the red tilde goes with the red arrow. That's why I was hoping we had colored chalk. So this is a technical axiom, and it's hardly ever used in exposition, but it's always sort of like underlying everything that we have. Okay, so if you have a Waldhausen category, then you have a Waldhausen construction. And what you get is a simplicial category out of this. Now I should give you an example of something which is a Waldhausen category. So an example of a Waldhausen category is finite based sets. I could give you much more complicated examples of a Waldhausen category, but this will work. So the idea is that this is just an inclusion, and A to B is an isomorphism or a bijection. Oh Lord, is there a hook? Of course it's at the far end. Okay, so now what have I done? I started with a bunch of motivating examples, and I have shown you a basic framework in which they fit, and now it's time to sort of define K-theory. So let's say of a ring R, for the sake of picking one of those examples. So here you would take K0 of R. And I think I did K0 of R somewhere over there. Yes, I did. Okay. But you also get groups Kn of R for all integers. So this is one way to think about algebraic K-theory. It's a sequence of abelian groups that fit into exact sequences and diagrams and whatnot. And another way that one can think about K-theory is to think of a topological space whose homotopy groups give you the K-theory groups. And the only thing that you would know up to this point in my lecture is if I take n equals to 0, you have to get this. And the idea is that this generalization is due to Quillen, but and the higher generalization is that you can form a spectrum. Now, what is a spectrum? A spectrum is a generalization of a topological space, and you can take homotopy groups of a spectrum. And the advantage of that is, let's say E is a spectrum. If you have a connective spectrum, you just get to talk about the positive homotopy groups, and if you have a non-connective spectrum, and you get to talk about the homotopy groups over all integers. Now, how many people in here know what a spectrum is? Okay, so that's maybe a third of you. So I will give you a definition which works and which is quick and dirty. So if you take a sequence of topological spaces and bonding maps, so it takes the suspension of E n and goes to the n plus first one. And in the world of topological spaces, I always have to say pointed, and I always forget to say pointed. If you want to take the suspension of a topological space, it's a good thing to take the suspension of a pointed topological space. And when you do that, there's an adjunction that maps in this from the suspension to here is in one-to-one correspondence with the maps from the E to the loop space. So one can think of this as any way, and then the pi n of E is a direct limit of pi n of E0 to pi n plus 1 of E1 to, well, dot, 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 pi n of E, no, pi I of E n plus I. So those are the homotopy groups of a spectrum. So the standard example of a spectrum is you start off with a sphere or a space. Start off with a space. Take the suspension of the space, the double suspension of the space, the triple suspension of the space. And if E to the n plus 1 is the n plus first suspension, there's a natural map from the suspension of the nth suspension to the n plus first suspension. So that would be a standard example. A? You're right. So where is my little clinging eraser? Thank you very much for that correction. Now, what have I done? Hang on for 1 second. I can't do that. Connective means exactly this, that the homotopy groups are 0 for negative groups. So the original constructions of algebraic K-theory are going to involve connective spectrum, and there's going to be a device which is going to give you a non-connective spectrum. So this device, if I take pi n of the K-theory spectrum,
Sorry, there's no actual definition.
I have not given you a definition.
But there is a definition of connective spectrum.
Oh yes, connective spectrum is a spectrum with this property.
No, that's not the property. That you just said we will only look at the positive ones. You didn't say the negative ones are 0. Now you're putting that as a condition,
Okay.
but that's not something one can check these days.
I thought that was what I had said, but if it wasn't, hopefully this is...
called connective where you only have the positive ones, and that there's a more general thing where you're positive and negative. Now you're saying you always have positive and negative, some are 0.
Okay, so here's I think what's going on. I'm using this adjective for clarification, just like one says an infinite group, an infinite set. One usually thinks that one could be finite, but not necessarily always. So if I say non-connective spectrum, I'm just using it to distinguish between these two. All right. I was going to say this, and I didn't get around to saying it. The spectrum K of R has pi n K of R equal to pi n of K of R equals Kn of R for all n in Z. And in fact, these if I'm thinking of a topological space, I can't really talk about its negative homotopy groups. So by going to this non-connective spectrum, then what I end up with are negative homotopy groups, but if I ignore the negative homotopy groups, then I get the same groups that I started with the topological space. Okay.
But in general, this K-theory spectrum is non-connected.
In general, it's non-connective. But the machines that we have, the Quillen and the Waldhausen machines, are going to give me a connective spectrum, and then you're going to have to do something extra to it to get a non-connective spectrum. And the step between here and here, I'm probably not going to talk about. Okay, so I wanted to give an example of a Waldhausen category. So I already gave one example, which is finite base sets. So any exact category, for example, coherent modules. So the little arrow with a tilde over it means isomorphism. And if you take the cofibrations, they're just the inclusions in the exact category which have the property that the co-kernel is also in your exact category. So for example, if I took a finitely generated projective and I included it in another finitely generated projective, the co-kernel may not be projective. But this is, if I want the co-kernel to stay in my category, then it has to be projective. So another example was any Quillen model category. Now I have to explain a little bit a Quillen model category is a way of modeling homotopy theory. So you have cofibrations and fibrations and weak equivalences. For the purposes of a Waldhausen category, we don't care about the fibrations at all. But if you just think about that. So here's a standard construction. Suppose I take a cofibration and I include it into B, and I map to 0. So that's allowed by my axiom. This one. What's the push out? So if I take the push out, then I get some object which I'm going to call B mod A, and that's allowed to be my co-kernel. And the fibrations are not co-kernels. Which is why we don't worry about fibrations. So once you have this notion here, we can form the category of extensions. And we can write them like that. And the reason why I can write them like that is because I can form a new category. I think I've done something funny here. I can keep going. And here's B2, and here's C2. And I can form diagrams like this. And if I take a specified length and I look at diagrams of that form, then you get a Waldhausen category for every single shape like that. So the condition is that if I pick any 2 points from here to here, and I look at the thing that's here, then from here to here is a cofibration, and from here to here is the co-kernel.
So what's the setting here? So Quillen, or Quillen model category, what's that?
So the point is that Quillen wrote so much work in 1968, and one of the things that he did was he formed a model category. Now, if you're in a department like mine with set theorists, a model category means something completely different. So this is just, there are two different definitions of model category in the literature. One has to do with logic and propositional logic, and the other one has to do with homotopy theory. And Quillen model category is the one which has to do with homotopy theory. And the basic definition of a Quillen model category is a category with cofibrations and weak equivalences and fibrations satisfying some axioms.
And then we can form one called causal categories out of extensions.
Once you have, so this is the third example. But I wanted to explain that the third example by introducing the notion of a co-kernel.
But my question is, where does the third example happen? So what's the assumption of the category where it makes sense?
If I start off with something which is already a Waldhausen category, then I can form this category of extensions. Okay, let's see, did I get lucky? I can reach that one. All right, so at this point yes, yes.
The diagrams, what do the bar of arrows mean?
So the, it means that the thing that you're mapping to is the co-kernel of a cofibration. Now at this point, what I've done is I've defined K0 of all of these categories. Well, I haven't really. So let me tell you what the K0 is. If I have a Quillen category, K0 of my, what's my category called? A. Is an abelian group with generators, classes of groups A, these are objects, and one relation, and that is for every short exact sequence, that is that the class of the middle is equal to the class of the left-hand side plus the class of the right-hand side. And for a Waldhausen category, and that is that if you have a weak equivalence between two objects, then it becomes an identity on the homotopy groups. I mean on the K0 groups. So so this is what K0 of everything is, and I want to note if I take bounded chain complexes of R modules, something like this. This is a Waldhausen category. And so I can say that the inclusion of one chain complex into the next is degree-wise weak equivalence. I mean, degree-wise cofibration. And so that means that, so here you have A0 going to A, well, if I have something like that, then I have something like this. So that would be a cofibration in the category of chain complexes, and a weak equivalence now hang on for 1 second. There's two notations that one uses when one talks about chain complexes. One notion is that you put subscripts and you have the differentials going down, and the other one is you put superscripts and the differentials going up. And there's a sort of a bijection between these two notations, and I've just messed them up. I've just interchanged them. So so if I write superscripts, you can translate that into subscripts with just changing the superscript to the bottom and adding a minus sign. So if you wanted, I could put an n and an n minus 1 as a subscript, but whatever. So if you have this, and now here's an exercise. If I take a chain complex, that you get an isomorphism of K0 groups by taking the Euler characteristic of a chain complex. And so now this works. In more generality, just replace chain complexes of R modules by chain complexes of objects in your favorite exact category, and the same definition works through, so you get an isomorphism on K-theory. Now the object of the game is to move now from abelian groups to topological spaces and beyond, but let's go to topological spaces first. So what I have to do is I have to construct a topological space, which is going to have the property that on homotopy groups is going to have the properties that I just outlined.
But you didn't finish this. You want to say quasi-isomorphism, though, so
Oh,
if quasi-isomorphism.
A dot to B dot is a quasi-isomorphism. Quasi-isomorphism, i.e., let's see, I'm doing subscripts. So it should mean that. So now I have to decide what to erase. And I think that the thing to erase I think that I can work here for a little while and then put it up. So if we have an exact category, so I said what an exact category was somewhere. It's a subcategory of an abelian category closed under extension. Then we form a new category. So let's give this category a name, A. And we form a new category with the same objects. And a morphism from A to B is the following thing. So a morphism is an inclusion of A as a sublayer into B. And what do I mean by all of this? I mean that B has a filtration by sub-objects, B prime and B double prime. And all of the inclusions are cofibrations. So that's a category. So the idea is that now K of A is B of this category. So if you want to compose two of these, if A is a sublevel of B and B is a sublevel of C, it's kind of obvious how A would be a sublevel of C, because you just have this filtration by C prime and C double prime, and then C prime mod C double prime has this additional filtration with the B's, and that's where A goes.
But it's not additive.
Sorry?
It's not additive. It was additive A and pure A is not.
It is actually, but that's not important. That's just a sort of a... okay, so there's a lot to be said about Quillen K-theory, and I have 25 minutes, and I'm not going to do it. So that's K-theory.
Sorry,
Yeah, hang on. Yes?
but before you erase, it's the degree-wise injective, right? This example.
Yes. So here's your chain complex A. Here's your chain complex B. A0 is to B0 is a cofibration. A1 to B1 is a cofibration. The diagram commutes. Yes?
It's not immediate for me that it preserves quality osmosis.
No, most of these things are not immediate. One has to do a little bit of work. But yes, it does.
Degree of, for example, split or something because it's just.
There are actually several different model structures that you could use, but I'm choosing the most naive one. And since I started off with R modules, I don't have to worry about the co-kernels being R modules or not. If I worried about bounded chain complexes of projective modules, I would have to include an additional condition that these are split in, vector bundles, that these would be split inclusions degree-wise so that the co-kernel would be a projective module. But that's sort of like going into the direction of, once you have one category which is going to model your K-theory, you have a whole plethora of categories with just little tweaks on the hypotheses, and they're all going to have the same K-theory. So I'm just choosing the one that's possible to do in an hour. And I think I made a mistake here. Where did I define? I'm actually off by one. Now, the point of showing you this explicit definition of what equivalent Q construction is that what you're doing is you're constructing a new category and you're taking the topological realization of that. So I didn't say this. That this B means the topological realization. So if you have a category, there's a natural way to form a topological space out of that category, and that's what B of the category is. And once I have a topological space, then I can talk about the loop space. And I've done this. And in fact, my categories always have an initial object, and so that's the base point of the realization. Okay. So Waldhausen form an extension category. The extensions should be the cofibration sequences A to B mod A. And just happily it's right under here so you can see what it is. And then morphisms are complicated. So we have a morphism from A to B to C, to B, A prime to B prime to C prime. And I want a morphism to go like this. But I also want the push out. So here I have a map like the axiom that I have up there. So I'm allowed to take A prime, union over A to B, and that maps to B prime. That's a weak equivalence. Okay. And now, this is called S1. It's the down from the push out to here, so there should be a prime there, yes. Thank you for keeping me honest. Okay, so I can form Sn, and it's going to be diagrams of this nature. And because I'm going to run out of letters of the alphabet very quickly, let's see here, the first, so this would be a 1, 0. This would be a 1, 1. And then here we have a 2, 1, and so on. And I'll let you fill in the details. So you form diagrams like this. So this is essentially a layer. With choices of A M modulo A n for every m greater or equal to n. Maybe I've used the letter n too many times. This n is not supposed to be the same as this n, so put an I there. So the morphisms are maps of these diagrams which satisfy a condition which is very similar to this. And I could write it down. You wouldn't really be able to digest it in a short period of time, and it's easier to look in the literature. So let me just leave the definition of the objects like this. And so now we get a simplicial category. So a simplicial category is a simplicial object in the category of categories. And so you have a family of objects S0 of A, S1 of A, S2 of A, etc. And we take the isomorphisms. Except we're not allowed to say the word isomorphism, we have to take weak equivalences. And you get a simplicial category. This one spells simplicial. And now the definition of the space. K of A is the realization, it's the loop space on the realization of the simplicial category we started off with. So here's the definition. And there you go. So one of the things that you learn from this is that A, the definition is combinatorial, and it's really something to do with category theory. And B, that it's complicated and it's hard to work with. So the bottom line is we do the constructions at the level of A, and all of this rest of this material rides along for the fun of it.
What do you mean by bake with equivalence?
This is the topological space. Well, you see, the weak equivalences Yes, you have to invert something, but it's already been done in machinery. I don't have to do any inverting anymore.
In which sense you take this weak equivalence, what do you mean by
Sorry?
You have a category, right?
Yes, I have a category, and I look at the category, the collection of weak equivalences in the category, and that's also a category because the weak equivalences in a Waldhausen category were a subcategory.
You take weak equivalence as a category.
As a category, yes. The key point that you should take out of this is that it's a complicated construction. You can work with it combinatorially, and you end up with a topological space with operations. Now, well, there it is. You know, my home blackboard, the red chalk doesn't erase. I'm glad to see that the red chalk erases well in this board. So let's step back and think about where we are. We have a category like bounded chain complexes of vector bundles or something like this. It's a Waldhausen category, and we have taken we've taken all of this detour in order to form a topological space whose homotopy groups give us the right thing. It's possible to make a connective spectrum out of it. I don't really want to go into that detail. It's possible to take that connective spectrum and make a non-connective spectrum out of it. I don't want to go into that detail because it would involve going into this detail, which I'm not going to go into. So this part of the game I'm just not going to talk about, other than let you know that it's there. So if you remember, well, here it's written, but you can't read it anymore. But if you remember that S1 was a category of extensions, and you have the source and the target of an extension. So I guess this is not a B, this is a C. If you take an extension A to B to C, this is an object of S1 of A. I take this as my source, I take this as my target, and I get two maps like this. And so the additivity theorem says that that's two copies of A. Now there are modifications. So if I don't just look at extensions of something by something, where everything is in my original category, if I restrict to a subcategory and I make the source in the subcategory and the target in the quotient category, then I can look at extensions, and what I get instead is the A prime and the A double prime. So the main application of this is that if you have functors F0, F1, F2 from A to B with, for every A, F0 of A goes to F1 of B of A, goes to F2 of A in B, then F1 is homotopic to F0 cross F1 as maps from the K theory of A to the K theory of A. So here's an example of that. So if I look at chain complexes, where the indexing just goes from 0 to n, then I can strip off the initial guy, and the quotient is everything which chain complexes go from 1 to n. Then I can strip off the next guy, and then I get complexes which go from 2 to n, and so on. And what you get is the K theory of this category of chain complexes from 0 to n of A is product from I equals 0 to n of the K theory of A.
So the previous line should go from A to B, K to B.
Yes, in fact. So let's see if I can modify that without getting myself into trouble. So if this is a B, yeah, that works. Okay, so then the consequence of that I care about is that if I look at the K theory of chain complexes which are bounded in A, K theory of A, and this is the Euler characteristic, and that's the homotopy equivalence. Now I see that my time is running short, so I want to point out there's an Eilenberg swindle. If I look at R mod, so what I've been doing up to this point is I've been sort of implicitly assuming that I was always talking about finitely generated R modules. If I don't talk about finitely generated R modules, let's see, I should use M for module. Then I have a natural exact sequence which takes the direct sum from 0 to infinity and just projects onto the sum from 1 to infinity, and the co-kernel is just the initial copy of M. And the additivity theorem says that this is equal to this plus this, but because F1 of M is naturally isomorphic to F2 of M by just shifting the indexing. And what you get is the K theory of this category is 0. So if you don't restrict yourself down to finitely generated things, and you allow infinitely generated things, you can pull off the little swindle, And it means that the K-theory is 0 and we're not talking about anything at all, which is why we don't talk about it. Okay. Where's the eraser? So if I have a map from A to B, then so a cylinder functor is something that I can write down in words or I can draw a picture. Topologically, this is a cylinder. You have a map from A into it, you have a map from B into it on this side. If I collapse A into here by homotopy equivalence, that's an identity. So assume that. Then approximation function, approximation says that if F from A to A prime is a weak equivalence in A, not if, but if and only if f of f from f of A to f of A prime is a weak equivalence in B. Then f of A, f takes A to B, induces f of A, k of A to k of B. And then the other property is localization. So I'm approximately 2 minutes from the ending of my lecture. And that says if B, W are weak equivalences, then you can form A, W, that's the subcategory of all A with 0 to A in W. And then the point is that the K-theory of this category relative to this, to the K-theory of A, relative to this weak equivalence to the K-theory of A, relative to this is a fibration. And by fibration, I mean you get a long exact sequence in homotopy groups. Now, why do we care about this? It's easier to go over here. So I'll give you one application. So S is a multiplicatively closed set in a ring R. And the category A is chain complexes of R projective R modules. Let's say projective modules. And W is well, let's see. You say the two things are equivalent, weakly equivalent if they're a quasi-isomorphism in the category of R modules. And the other equivalence is that they're weak quasi-isomorphism in the localized category. So what is the A of W? That's chain complexes of R modules. So let's say M dot and if I take the localization, this is quasi-isomorphic to 0 in the ring S inverse of R, chain complexes of S inverse of R. So we make a definition. K theory of R on S is the K theory of this category. And now you get a vibration sequence. And that gives you long exact sequences. Which allow you to compare the K theory of one ring to the K theory of another ring. And the same trick works for a subscheme Z contained in X, where the K theory of X on Z is coming from chain complexes which are bounded of X modules on X, which are quasi-isomorphism to 0 in category of chain complexes on Z. So this is the algebraic variety version of this theorem for rings. And I've gone over time, and I apologize you didn't ding me.
I was going to, but I was being...
Go ahead and ding me. Thank you.
All right.
Yes.
Please clarify where you're assuming the existence of cylinder.
Is it just something like you have enough
The cylinder functor comes into play when you want to sort of build short exact sequences and extensions in these categories.
Yeah, so modular.
So it's a technical machine that allows you to do something. So, for example, if you have a map of chain complexes, there's a natural cone complex that you can form in a functorial way, and that cone complex is functioning as the cylinder complex. And if you've ever worked with chain complexes, you know that working with a cone is a very useful trick. And so it allows you to prove lots of things. So it's a technical device which allows you to prove theorems.
Yeah, but for me, as I understand for the moment, it seems to me that you
because in K-theory, in some weak sense, you have a collection of exact sequences, and you invert a map like this. But if you have cylinder function, that is, roughly speaking, you can invert any map.
What a cylinder functor does is if you start off with a map from A to B, it allows you to make a long exact sequence.
It's an arbitrary map, right?
An arbitrary map A to B fits into a long exact sequence, where the third thing is the cylinder.
Yeah, so that is if you modulo weak equivalence, or I mean, if you invert the weak equivalence in infinity category sense, then any map fits into that is to say that any map fits into a cofibration.
Okay, what you're observing is that if you have a map from A to B, you can replace B by something larger,
Yeah.
namely.
And it's not larger in the sense, or it's the same in the sense of.
Oh, I see. I've done something silly. I didn't tell you what the cone is. If I take this construction and I smash out A to a point, then you get a cone. And that cone construction is, roughly speaking, the analog of what you're talking about. So once you have the cylinder function, you can push out along the map from A to 0, and you get the cone. The cone is this, right? So here's A sitting inside of B. So if you have a map from A to B, then you can talk about the cone. And the cone is the thing that you use in homological algebra. And being able to say that the cone exists so that you can form diagrams, that's the technical advantage of having the cylinder functor. Other questions?